Okay. Hi, good afternoon, everyone. My name is Mehak Mahajan, and I work in software engineering in Broadcom's networking business unit. I have the privilege of presenting with Jasmeet Bagga, who is also part of software engineering for FBOSS team at Meta. And today we'll be talking about cable length measurement. As a part of this, we will discuss about why is cable length measurement becoming relevant again, the data center velocity that is leading to a lot of gotchas if you don't really get this right, the importance of cable length measurement in the large networks that Meta has been deploying and describing to the rest of the community as well over the past couple of years. A deployment story, how things can go wrong, how things did go wrong, and the cost associated with it in order to correct something like this. And finally, the feature implementation workflow and the SAI enhancement that we will be bringing to the community. So let's talk about cables at this point. So I did not in my wildest dream ever imagine that I'd be standing on a podium and talk to an Ethernet-centric audience about the Ethernet cable in the year 2025. Cables are at the heart of the interconnect for any Ethernet network. But for the decades for which the data centers are being deployed, we have never really been talking about their length. What you have been talking about is the choices between the DAC and the optics cables, the associated power, the associated costs, and other things. But the AI has changed that. Length of the cable is suddenly extremely relevant. As these AI infrastructures are growing in order to meet the ever-increasing or ever-larger models and the training clusters, the data center footprint itself is becoming much larger. So an important operational challenge is emerging from the physical reality of the network design that is associated with the performance that you can get out of an AI fabric. Larger data centers means larger cables. Go figure, right? So a minor detail, such as the cable length, is now impacting the performance that you're going to get as vast amounts of data shuffles between this AI fabric. Right. Why is this so? Cable length directly dictates or impacts the propagation delay, which in fact directly influences the buffer provisioning. Historically, it's not like buffers are new to us, right? But in traditional data centers, any misgivings in the length calculation were not a big deal because the switches had sufficient buffer to absorb this kind of miscalculations. But with the bursty traffic that is a characteristic of AI workloads and the vast volumes of data that we keep talking about, you can no longer be forgiven for miscalculations in cable length. And at the heart of this is the desire and the intense need of getting the right buffer sizing. Under-provision your buffers, and you're going to see buffer overruns, packet drops, packet retransmissions, stalling your collective operations, thereby reducing the effective throughput that you're going to get out of the network. Over-provision your buffers, and you are going to see a larger resident time for that packet on the network. You're going to see an increase in the end-to-end latency. You're also going to see a degradation in the overall efficiency of the network. So in order to get the right performance out of your data centers so that you can ensure that you continue to operate at peak efficiency and sustain your throughput, you must calculate your cable length accurately. So no longer is this just a function of engineering efficiency. It is actually a direct performance and cost optimization lever.
Thank you, Mehak. So with this, let me set some context of, and set some, add some flesh to this story. Why did this become important, and why we are motivated to present a vendor-agnostic solution that works across different vendors and across different deployments? So in the last, couple of days, you've seen this slide probably many times. We presented this as our highest, the most scalable data centers that we are building. And there is Prometheus, which is a gigawatt plus data center coming fully online in 2026. Parts of it are online today. And then Hyperion, which is following soon after, which is a 5 gigawatt cluster. Just to set some context, we've been through the Facebook ramp up of 3.5 billion daily active users, and through the mobile revolution that happened while Facebook scaled. We built data centers back then as well, and they were at a rapid speed. However, the speed and scale at which we are building now is truly different. Truly, it's much more than when we were going through those phases. So in the age of AI, the demand is constantly to build them faster, build them bigger. The more GPUs you can put in close proximity, and now the close proximity is also getting over multiple kilometers, the better it is. So the more GPUs that can train together, the better it is. However, there is a vital component to data center builds, which is the fiber layout and the fiber design. And this fiber design is done a priori, because even before the data center is built, the fiber needs to be planned, what the layout is, and then the construction happens, the ordering happens, and finally the execution happens. This is a lot of projections done upfront. While we are good at it, at this scale and speed, mistakes can happen. So simultaneously, while this was going on, we were building a network which was actually quite dependent on fiber lengths. So enter DSF, disaggregated scheduled fabric. This is a VOQ-based system, which we have again talked about in many presentations at OCP before, where we are doing end-to-end scheduling. Here, for example, this diagram shows a two-stage DSF network capable of supporting 18.5K GPUs attached to it. The speed at which we developed DSF was also quite significant. Last year, near the end of the last year, we just had our first single-stage 4K GPU clusters coming online, and within a few months, we had this dual-stage cluster coming online, which is an order of magnitude more complexity than the single-stage. Order of more magnitude more complexity for the software, for the chips, also for the fiber layouts. The requirements for how far these endpoints could be became even tighter. And DSF is at the heart of the Prometheus build. So DSF is running in Prometheus right now. A lot of the Prometheus build till now is DSF. DSF has strict requirements for end-to-end cable length, how far edge VOQ switch can be from another. Also, how far an edge VOQ switch can be from a fabric element. And these requirements get stricter with dual stage. Then there is a hyperport, which is a data center interconnect, FAT port, or a bonded link port. You call it what you want. It's a 3.2 tera port that is built by bonding 4 into 800 gig L1 ports. And it behaves like an L1 port. So it is freely spraying bits amongst those 4 by 800 gig links and getting you perfect load balancing at the L1 level. However, the flip side of that is the skew between those member ports needs to be controlled, because there is an ordering that is happening on the other side. If you skew too much, then the buffering requirements go up. So you need to get this right. And we were very paranoid about these lengths. So we had built a system in DSF from day one where these lengths would be measured, and we would check them once the deployments had started. However, it's not just DSF, right? We are also connecting shallow buffer-based switches called non-scheduled fabric across long data center interconnect links. These data center interconnect links could be tens of kilometers apart. So as Mehak was pointing out, if you get these wrong, you have to either over-provision your buffer, which in shallow buffer switches is expensive, or you under-provision and get packet loss. Also, there is a latency component that adds to it. If you get these cable lengths incorrect, if you're tens of kilometers apart, you could be 1 kilometer off. You would put an effect on the latency as well. So it is important outside of DSF also to get these right. Okay. Finally, a war story. So because we were paranoid, we were measuring this all the time. And as the things were getting deployed, we suddenly noticed that our cable length monitoring detected that we were out of spec. While we were developing this product, even the requirements got tighter. We realized we had to, for the faulty links, we had to build in some error correction, and that reduced the distances that were allowed. So we got hit with a double whammy, where we detected that we had this accelerated schedule, which actually got us a little bit out of spec, and then we added this error correction, which got us more out of spec. Luckily, we had this monitoring. We detected early on that we are out of spec. This actually triggered a very painful process of recabling and figuring out how to get back into spec. However, it is much better than discovering this later on. Imagine how we would have discovered this later on. We would have discovered that certain times we are getting loss, and now that loss is unexplained. So we would have to really go and dig in, diagnose every other cause of loss, and then finally ask somebody to go measure on the floor and figure out, hey, actually, are we within spec or not? So the fact that this detected actually saved the product. So without this, it could have actually gone to production and discovered much later on and become an unreliable product. So since we had built this for DSF, we wanted to propose, and which is, this solution in DSF is a proprietary solution. We wanted to propose a vendor-agnostic, platform-neutral solution which could work across vendors, which could work across Ethernet links, and so on. So Mehak, in the next few slides, will present that solution. We urge you to take the solution on. The spec, et cetera, will be provided as well, and we urge you to participate.
Thank you. So for such a critical feature, but yet such an understated feature, the implementation is also very, very simple, to be honest, right? It's surprising that we and others haven't already done it, right? Well, we did it, so yes. The link, it's as simple as this, right? Your link comes up in the hardware. The link up notifications are already getting sent up the stack to the software because there's already a lot of components that need to react to this link up notification. Now, as this link up notification makes it through the SAI and the SDK stack, the SAI triggers a request to the SDK to trigger a cable length detection or an auto cable length detection. Upon getting this request, the SDK creates a request message and sends it to the target port, which ends up going over the actual cable, reaching the other peer. Upon receiving this, the peer copies the timestamps, creates a response, and sends it back over the very port that it receives. And then the requester takes out all the timestamps and calculates the cable or the propagation delay associated. This cable length is then stored in the SDK or cached in the SDK. So please note you are re-triggering a cable length detection every time that the link comes up because we have no way of knowing that you went and swapped the cable. So it gets triggered every time that the link up happens. At any point in time when the NOS wants to know what is that cable length because you got a packet loss or there's an unexplained loss that you do not know why it happened and you want to eliminate the cable length or the buffer sizing as a consequence of it, you query the SAI or the SDK through the SAI, asking for the cable length, and the SAI will return the cached value to you. Here is a little bit of more detail on how the actual exchange of packets is happening. You might see over here that we've said P delay request and P delay response, but don't worry, you do not need PTP clock synchronization for any of this. The only thing that we have done is that we have borrowed the PTP packet format so that we don't go about inventing another new packet format for everybody else to learn about. And it's already available, why not use it? One thing that you do need to ensure is that you do need to have hardware-based timestamping available on your switch because you want to ensure that the packet gets hardware timestamped so as to reduce or take out the software propagation delay, else it will skew your cable length measurements. As we mentioned, it's a simple SAI extension that we introduced in order to do this. Most of the magic is already being done by the SDKs. You just need to query it and get it upon link up notification, and you will just go ahead and get the values anytime that you need this value. We will be taking this to the SAI community, and given that I think we have sufficiently explained and possibly overemphasized the need for cable length measurement and precise cable length measurement, we request that as we take this to the community, we get your support to approve it. Thank you.
We can take questions if there are any.
Yeah, please line up for questions.
Excuse me. Once the cable length is detected, are you already have implementation of like changing the buffer size automatically? Do you have like a formula for that, or?
So we won't change it dynamically. Right now, we don't change it dynamically. We actually we have planned for certain cable lengths. We expect those cable lengths to be within an error of margin to be as is. So we don't change the buffer size dynamically. However, we detect that we are not going as planned, and we signal and we catch this early on, and get in touch with our deployment folks and say, hey, we need to fix this.
I see. And this is more PFC and some congestion control focused enhancement. I guess.
Exactly. I mean, it could be different. Like for example, in DSF, it's other protocols and other things that are getting affected by it. But yes, you can call it for NSF, it's PFC and other buffer settings.
I see.
So anytime that you have buffer sizing, right? Like for VOQs, you have buffer sizing. For PFC, you would have buffer sizing.
Right.
Cable length measurement is something that would influence the buffer sizing.
I see. And you said like within a spec means like a certain quanta value that you want to be inside of that time window.
Yeah, I mean, we want to be, let's say, we've laid out the fiber plan. Now that fiber plan says we expect this segment to be 500 meters apart. We don't want it to be a kilometer apart. Right. So we would say, maybe 500 to 525 is okay. But if it's beyond that, we would signal and detect a fault.
Okay, thank you. Yeah.
I wanted to check how does it work between two different ASIC vendors? Like the timestamp, is that it's an open source way of putting a timestamp, or how is it?
The PTP header, PTP packets are standard open format. So as long as they can speak PTP to each other.
So we need to have PTP running for this?
You don't need to have.
You do not need to have PTP running for this. You just need to have hardware timestamping available on your ASIC for this. And the reason for us to pick up an available frame format was precisely this. In order to support an open ecosystem, that anybody can actually go ahead and implement this on their side of the SDK, and you can have interoperability between vendors, just to support the whole open ecosystem that goes along with it.
Okay, thank you.
Think of it this way, right? Both sides have enabled PTP timestamping. That's it. There is no central coordination. There is no central clock. In fact, we explicitly designed this to not require a central PTP, master clock enabled for this, because that's a deployment. That requires more deployment challenges. Yeah. So both sides will timestamp, and then you detect the delta, and you can see where the delay is.
Okay, thank you.
Hi, what is the error that is expected in this methodology, and how do you know that the error of the methodology won't affect the results?
So we actually, there is the errors can be due to, there is some delay in the pipeline as well, which we rely on the ASIC vendor to get right and, get us what the tolerance is. We actually physically measured this after the fact and said, are we within spec? Actually, when we got the first readings, honestly, we thought this is wrong, and it turned out to be correct. We did measure this.
So it depends upon where in the pipeline your hardware timestamp is happening, is what Jasmeet is alluding to, right? If it's happening right when you enter into the port macro, absolutely it will be right at the entry of the switch. But any kind of delay, because these delays and these RTTs that you're calculating is in nanoseconds, right? It's not really in milliseconds and seconds. So any kind of a skew would impact what kind of cable length that you would detect. And so that is what he's saying, that you need to work with the ASIC vendor to understand where in the pipeline is the hardware timestamping happening and what is the general latency that it takes from getting into the port to the place where the timestamping is happening. And if that is, and ensure that you correct for that in your cable length measurement.
Thank you. And very quick follow-up. When you're sort of contributing to the open standard, would you consider contributing the measurements that you've done? I imagine you have a fairly large data set of what cable lengths and cable configurations you've measured, the what switch ASICs you've measured, and the delays that you've seen. I think that would be very helpful to the community.
So we've already shared what we have done with DSF, right? The ASICs there are well known. We've said that before. And the specs with the ASIC for how long they can be, I think Broadcom has already shared that.
Yes.
There are distances that are within this spec, and we got it right down to less than 10 meter of error. So let me say that, it was less than 10 meter of error.
Okay, very impressive. Thank you.
Hi, do we still have time for one question? Okay. So you mentioned that you only need the hardware to do PTP stamping, but not synchronization. Is that what you
That's
said?
correct.
Yeah.
Then what if one side's clock is way ahead of the other side's clock? How do you measure
The
that?
calculation actually accounts for the clock skew.
I mean, how? Do you have that in slides?
Pardon?
Do you have that information in the slides?
Yes. I mean, if you look at the calculation that we have shown, it's a very simple mathematical calculation. You will see that the subtraction automatically takes into account the skews that can happen on both sides, and they cancel out.
Okay, thank you.
Thank you.
All right, I don't see any other questions. Thank you, Jasmeet and Mike.
Thank you.
Thank you.